Our team, Calc Intelligence, has partnered with Excel for many years. This talk is going to talk about our past work on incubating LAMBDA and the concepts of Excel as a programming language, our present work on the LAMBDA editor, and finally I'm going to talk about some future directions that we're very excited about. We are a team of researchers, engineers and designers. Calc Intelligence, our mission is to create a trustworthy collaborator and teacher to empower more people to get more value from data. This is our building near Cambridge train station. Here's a photo we're happy about, remembering happy days when we could work together. This is a warm-up exercise for a design jam we were doing on sheet-defined functions, something I'll tell you about later. And it shows some of the Excel team with some of our team having a bit of fun. We have this lovely quote from Dave Gaynor, Vice President for Calc in Office and responsible for Excel. He says, "Simply put, Microsoft researchers are now a core part of the Excel team, helping to create the product's future." Let me tell you about Project Yellow. This is a project to think about Excel as a programming language, and it's been a long-term partnership between us and Excel. This is Bonnie Nardi, an eminent HCI, human-computer interaction researcher. And back in the 90s, she was one of the first people to realize that what people were doing with spreadsheets was programming. She came up with the phrase end-user programming, and that describes programming to achieve the result of a program primarily for personal rather than public use. Amy Coe and others came up with another characterization. End-user programmers are secretaries, accountants, children, teachers, interaction designers, scientists, or anyone who finds themselves writing programs to support their work or hobbies. What are end-user programs like? Well, there was an amazing treasure trove of spreadsheets uncovered in a trove of emails that were placed in the public domain following the legal difficulties that Enron got into back in 2001. So those emails that were made available included about 15,000 spreadsheets. And some researchers, Felina Hermans and Emerson Murphy-Hill, did an exploratory data analysis of those spreadsheets. And it revealed fascinating information about the way people use spreadsheets. They found, for instance, that about half of all spreadsheets contain formulas. That also means that half don't. So, Excel is a very versatile business and presentation tool. People use tables, charts, pivot tables without necessarily writing formulas. So people get a lot done in spreadsheets without writing any code themselves. But on the other hand, half spreadsheets do contain formulas. So it really is a programming activity, building spreadsheets. On the other hand, they found that most formulas are actually pretty simple. So those functions, sum, plus, minus, times, divide, and if, cover half of all the functions you discover in spreadsheets. So the conclusion from this is that most end-user programmers write very simple formulas. These people are not computer enthusiasts. They're not primarily interested in building complex programs for their own sake. They tend to write quite simple formulas. There are ambitious spreadsheets with thousands of formulas in them, sometimes developed over many years by skilled experts. There's a nice cartoon from XKCD about the complexity of programs. You start on the left with something very similar like left pad and quicksort, getting more complicated, Git, self-driving car. But on the far right, we have a sprawling Excel spreadsheet built up over 20 years by a church group in Nebraska to coordinate their scheduling. I think we've all seen very complex spreadsheets. Spreadsheets are code, and spreadsheets are programming languages, but we have to admit it's an unusual kind of programming language. Here's a comparison. On the left-hand side, you've got traditional programming. On the right-hand side, you've got Excel. So on the left-hand side, traditionally, you'd have professional programmers compared to end-user domain experts writing code in Excel. On the left, programmers tend to write code, concentrating on that, not looking at the data, whereas in Excel, data is first, and the code, the formulas are actually invisible. On the left, traditional programming is about edit, compiling, and running. On the right, Excel is always live. You edit the formula, you edit the data, it recalcs at once. In traditional programming, programs are laid out in time. You think about writing loops that iterate over time, whereas In Excel, programs are laid out in space. You know, the equivalent of a loop is like drag filling a formula over a range of cells in the grid. It's also rather a weak programming language. So in traditional programming, we've rich data arrays and records. You can define functions whenever you want. You can save your code out to GitHub and collaborate with others there. On the other hand, in Excel, until recently, we've been limited to scalar data only in cells. You know, only a number or a string could be in a cell. There's a fixed library of only about 600 built-in functions, and there's no real equivalent to GitHub. You sort of mail spreadsheets around. Still, spreadsheets are very useful and accessible and friendly, so people can build these ambitious applications, although the kind of engineering properties are rather weak, and you get a lot of duplicated formulas and copies of worksheets. And the result of all this is that although spreadsheets are very powerful, they're also unfortunately rather riddled with errors, and so we've got a litany of awkward, unfortunate headlines here. What can we do about that? Well, researchers here at MSR Cambridge about 20 years ago started to think seriously about how to transform spreadsheets into a full programming language. And one of the core ideas they came up with, and this is led by Simon Peyton-Jones, who's still in our team, it was the idea of a sheet-defined function. And here's a very simple illustration of what that might be. On the right, we've got a bit of grid that's defining an average. Here's the input, these 5 cells in B3 down to B7. And then we've got a cell over here that counts the number 5, and a cell over here that adds them up, getting 42, and a cell here that does the division to get the average. So that's an example calculation in the grid. And the idea of a sheet-defined function is that we can give this a name, call it average, say. I know that already exists, but this is really just a simple example. So we introduce a new name, average, for this calculation, and say that the yellow range is the input and the green cell is the output. And then we can, if we were to do that, then we can use this new average function like any other and say equals average. And what Excel would do is take the data in B3 to B7 and sort of make a copy of the grid, put that data in there, and calculate what the output would be by calculating the whole grid, and then returning whatever is in E5. So that's the basic idea of a sheet-defined function. That was research that was done here, and about 6 or 7 years ago, the Excel team decided to pick up on this research and create a new project called Project Yellow that would try to transform Excel to eliminate some of the problems that have been experienced by people building complex spreadsheets. So the goal of Project Yellow was to remove the glass ceiling that limits the scope and reach of what a domain expert can do with Excel. And one key point was to make Excel functions reflect the abstractions of our end users by allowing end users to define new functions using ordinary formulas, like using sheet-defined functions, or indeed like using LAMBDA that is now available. And the second big principle of Project Yellow was to make the data values of Excel reflect the data types of our end users' domains by adding arrays, vectors, records, and even domain-specific data types implemented by third parties. So this project is well underway, and we have been collaborating with the Excel team on Project Yellow from the start. By a few years ago, 2018, we announced dynamic arrays at Microsoft's event Ignite in that year. Dynamic arrays allow a single cell to contain an array that spills out. So you see here in B5, we had a sort function that's sorting this range on the left, and the result of that spills out, as we'll see, right? So we say equals sort, that range, and the result spills from the array. And here we got a function unique that removes the duplicate values from that range. And here on the right, we've got a function filter that filters out just the names of people who are eating vegetarian food or wanting vegetarian food. So that was that was the second principle that I was talking about, of enriching the data types that people can manipulate directly within Excel. And that was announced publicly in 2018. Meanwhile, in Cambridge in 2018, our team was working hard with Excel on bringing LAMBDA to life. So this is a photo of taking place during discussions we were having when some members of the Excel team, Andy here and Jeff here, were visiting Cambridge, and it was Simon's birthday, so we got a nice cake, and I took a photo of the team here. And this is a nice record because Claudio was an engineer in our team at that point, and he worked really closely with Andy on implementing lambdas directly within the product. I like this photo as a kind of gestation of Lambda in Excel. Fast forward to today, Lambda is out. It got a very positive reception from Excel users. Satya Nadella tweeted about it, and it even made it into XKCD, which is pretty neat. Why is Lambda so important? Well, I'd say there's 3 R's. R for readable. Lambda makes workbooks more readable because you can capture complex logic in a single formula. It makes your logic more reusable because once you've turned it into a Lambda formula and given it a name, it's easy to call it from other places. And Lambda also allows recursive calculations to be done inside the formula language. And so it makes the formula language Turing complete. I'm now going to hand over to Jack, who's going to tell us about the Lambda editor we're developing in our lab, which makes it much easier to develop new lambdas.
Hi, I'm Jack, a researcher in Calc Intelligence. I'm going to be talking about the Lambda editor, which is a research prototype for authoring lambdas in Excel. We built the Lambda editor to try and understand how users are going to program in spreadsheets and how they might share their code that they write. I'll be going through an example that shows you how to create a function for formatting strings as different titles.
We've got a fresh workbook, so we're going to go ahead and open up the Lambda editor. Here we have the add-in, which is an interface to the name manager, but it's an interface that is really designed for writing lambdas and also sharing them. So as I said, we're going to be going through the example of taking a string and converting it to different case styles. I won't go through all of the details of this function, but I will cover some key components, and in particular I will cover the component which is taking the string and splitting it into words, because that will let us process each word individually. And for us to do that, we need a text split function, which given a delimiter is going to split the text according to the delimiter. And in this particular instance, we want to split it according to a space to get the words. I'm going to develop this in an interactive way using both the grid and the editor. So I'm going to start by creating some inputs to test, and I'll use the same string that we have in the grid. So we're going to put writing some lambdas, and I'm going to call this arg. And we're developing a split function, so I want a delimiter, and it's going to be an empty space, and we'll call this delimiter. Now I can sync this into the name manager, and it will be available in the grid. The process of implementing this function is really going to come down to taking the characters in the string, finding the positions where the delimiter occurs, and then extracting pieces of string between 2 delimiters. In order to make this process uniform, we're going to put delimiters at each end of the input string, which means that we always have at least one piece of string that is between 2 delimiters. So let me add this piece of pre-processing. So I'm going to create an input string, and it's just going to be delimiter, then arg, and then delimiter. Add that, and then we will see that that's the same but with a space at the front and back. Now we need to start processing the input on a character basis, so we'll start by just getting all of the valid positions of characters in the string. So we want to generate an array of numbers, and we can do that using sequence. So we want a sequence from 1 up to the length of string, and I'm going to call this positions. That's the positions. Now we want the individual characters, and so for each position we want to get the character in the string. So that's an iteration over every position, and we can use one of the new array helper functions, which is map. So we're going to map over the positions, and map takes a lambda that takes an individual element of the array and then returns a new element. So we're going to take a position I, and we are going to extract from string character I, and there's only one character. Call this characters. So let's sync this, and now we can test it out in the grid. So we've got positions, that's our list of positions, and then we've got our characters. And you can see that we have the space at the beginning and end. Now we have the characters, we want to find out which character is a delimiter. So this is another map, this time over the characters, and we want to return true or false depending on whether we have a delimiter. So we're going to write a map over the characters. We need our lambda function, and this is going to take a character now, and we're going to compare character to the delimiter. And we're using case sensitive matching. So this gives us an array of booleans where if an element is true, it means it's a delimiter. We can test that, and we can see, yep, true for there, and then false, and so on. Now we have that, we want to find the positions where a delimiter begins, because this marks where we start and end collecting text. So this is really just finding the positions where a delimiter exists, and so this is just a filter on positions. So I'm going to filter positions by delimiters, and we will call this starts, because this is where we start each new word in the output. Sync this and then evaluate it, and we can see we've got a delimiter at 1, at 9, 14 and 23, and that means that we want to extract text between 1 and 9, between 9 and 14, and between 14 and 23. So this is another array processing step that we need to do, but it's not a map, because we don't want an element for each one of these, we want an element in between each pair. So we need more control over the array, and for that we're going to use makeArray, another new function. So makeArray takes the dimensions of the output array, and the dimensions are going to be the number of elements in starts minus 1, because we want the in between each delimiter. We're only going to have one column, and then we're going to have a lambda that takes 2 arguments, which is the position in the array we're generating. Because this is just a row with one column, we don't care about the column, so we can just make that an underscore. Now we want to extract the start and end positions from our array, so I'm going to use a let just to hold these calculations. So our start is going to be an index into starts at position I, and then our end is going to be the next position on, so I plus 1. And so this is the difference between map and makeArray. With map you are just given the element directly. Here we compute with positions, and so we can access different elements. So now we have the start and end of the delimiters. Now we want to extract the text between them. So it's going to be mid, and it's going to be string, and we want start plus 1 because we don't want to include the delimiter. And then it's end minus start minus 1. That's the number of characters we're extracting. Now let me synchronize that. Oh, I need to give it a name. I'll call this result, because this is the result of the text split. And so now we have the individual words. And if I wanted to modify this, let's try that. Then everything recalculates, and so we kind of see the nice process of developing in the grid and using the editor. Let's fix that up. Of course, this isn't a function, this is just us doing the individual steps. What we really want to do is take these names and then package them up in a Lambda using each one of these name manager names as a let name. And then that way we can reuse it as a function. So one thing I didn't talk about was the editor view. And so this is an alternate representation of the name manager, which is more like a code editor. So if we look here, we can see that here we have a single file that has all of our names that we defined before. Now what we want to do is we want to take these and we want to package it up into a single Lambda. And so I've written that one earlier on, and I can copy that in. And so this is our split on Lambda, and you can see that here the things that were previously names we've now just made into let definitions. So let me clear these and then synchronize, and now we can call split on a string and a delimiter, and we get our split input. Now this of course isn't the function that's going to capitalize or sort the cases out in our input, so we need a lot more for that. Luckily I've prepared that one earlier, and actually I prepared that in a whole file, and I can just copy that in and create a new namespace. And so that's what I'm going to do. So I'm just going to clear this, and then I'm going to create a new namespace, and I'm going to call this text. And then I will copy in the full definitions that I've written earlier. And then we can synchronize this. And if we look at the manager view, what we see is that each name now has this prefix, and so in the editor view, to make it easier to work with these things, we allow you to split names up by a prefix, and then when they get synced into the name manager, they all have a single hierarchy of names which are prefixed with the namespace. So just to go over these functions quickly, we can see we have this sentence case which uses our format title function, and this is a Lambda that's going to split into words, and then it's going to construct an array by formatting the first word with our head function, formatting the rest of the words with our tail function, and then joining them together. And for sentence case, for the first word it's proper, so we capitalize the first letter, and everything else is lower. Then for our title case down here, we format it, again the first word is proper, but then the rest of the words we have this other helper function getWord. And so this function looks through a dictionary of words, and if it matches it returns that, otherwise it will capitalize it using proper. So now I can test that out in the grid. So I've got text dot sentence case A2, and then I've got text dot title case, and that gives me the expected output. We've created our lambdas for formatting strings as titles, and before we use it we should really test it. So I'm going to go through some small test lambdas, but I'm also going to show how the Lambda editor lets you pull in definitions from GitHub. So you'll see in the top right of the editor there's my name here, and that's because I'm logged into my GitHub account. And that means that I can use the Lambda hub, which is a way of bookmarking or favoriting collections of lambdas stored on GitHub. So if I open up the Lambda hub and I use a subscription, you'll see I have a subscription here for test, and this points to a gist on GitHub. I can import that, and it's going to create a new namespace for test and insert that into the editor. And if you go to that URL on GitHub, you'll see I have the corresponding definitions there. So what this collection of lambdas does, the most important one is test.cases. It's a lambda. It's going to take a description of the test that we're running. It's going to take your test cases, which is a table of inputs and expected outputs. It takes a test function, that's the thing you're testing, and then it takes a compare function, and this is an optional parameter indicated by the square brackets. By default, if we don't give a compare function, we just use Excel's equality. But if we do provide one, then we use that. So we use these optional parameters and the isOmitted function in order to create a comparison. So let me synchronize that and let's go through an example. So I'm going to write some test cases. So let's do hello world. The fat cat sat on the mat. Here are some test cases. So let's test out our title case function. And so we expect that to look like this. And now we can call our test cases function. So test.cases. We give it a description, title case test. We give it our input output table. We then give it a lambda, which is going to execute on each input output pair. So this is taking a lambda as a value. And we want to test out our title case function. And then lastly, we want to give it a comparison function. So even though this is optional, because we're comparing strings, we want to use case sensitive matching. So I'm going to create a lambda. It takes two parameters and it's going to run exact on those two parameters. Now my test has failed. It expected the fat cat sat on the mat in this form to be equal to this, but it's not. It's not that the function is wrong, it's just that my test case actually isn't correct. So let me put this properly into title case. And then last but not least, and so now all of my cases have passed. And we can do a couple of sentence case tests. So let's copy these. And we can run our test cases again, test.cases. And then we want to give it our lambda to evaluate. And then again, we need a special compare function for text. And that also passed all the tests. So that's the Lambda editor. So we have a manager view, which displays the names in the name manager in a prettified way. We have the dual representation of the editor, which has namespaces for organizing names, with the index being the special top level. And then we also have integration with GitHub. So you can have a set of subscriptions so that whenever you open the editor in any different workbook, if you're logged into GitHub, you can pull those in and start using them immediately. And if I want to make changes, I can do that too. So for instance, I might want to put just a comment at the top of this file. I can then re-upload this to GitHub. And now if I look online and refresh, my comment has been added. And so anywhere that I'm using this, I can pull that in.
Next, I'm going to tell you about 3 different research papers that we worked on in our team. First up, I'm going to tell you a bit about uncertain values. This is an aspiration we've had for a long time in Project Yellow, to be able to store an uncertain value in a cell. On the left is how you would do a calculation of compound interest today in Excel, where we're forced to say that in the future we think the APR is going to be exactly 10% in each of the next 4 months. And that's fine, and we'll get a particular answer for the accumulation of the capital over that time. On the right is what we would like to be able to do in Excel, to store uncertain values in cells as inputs and get uncertain values as outputs. So the 4 cells in column E are uncertain predictions, if you like, of what we think the APR might be. We think that it's most likely to be 0.1, but it might be as low as 0 and as high as 0.2, and tailing off as we move away from the midpoint. So that's like 4 uncertain values we put into the cell, and then that propagates. So this calculation of interest over here is uncertain, and so is the final result. So we think the midpoint is 1033, which is the same as what we get out of the deterministic calculation on the left. But the great benefit on the right is we get an indication of what the spread might be, of what the min and the max could be. Now, if we could, now we have this actually running in Excel. So if I bring that up, here we go. There we are. I've got an example. So I've implemented a function, a new function called xsum as a lambda, and it can calculate with uncertain values. So here is someone's budget, where their income is 1,000 plus 1,000, and it's calculated there. And these items here are their expenses. And this one here for utilities is actually expressed as a range that Clara, who is building the spreadsheet, is estimating that the utility bill is going to be between 50 and 150. And so that means that when we calculate the expenses, it's coming out as a mean of being 1986. And then when we calculate the balance using xsum, so you see xsum is taking the sum of all these items, including the uncertain values. Whoops-a-daisy. We get a mean of 15, and we get a chance. We can calculate using the spread in this uncertain value. We get the chance of whether she's going to be in the black, and it's 3/4. So Clara will think, yeah, that's probably worth taking the chance. But say if the utilities were likely to be a bit higher, maybe instead of between 50 and 150, maybe it was between 50 and 450, then the expenses go up and the balance goes down, and now there's a very slim chance of being above 0. And so using Excel, she can now decide maybe it's not worth taking the risk. I won't buy the sofa. Over on the right, the implementation of xsum is done using the LAMBDA editor, and it's a few hundred lines. We actually have a parser using recursion to parse these formulas and to evaluate them. And we use Monte Carlo simulations to represent the uncertain values and to get these estimates of the chances of breaking even. So it's really cool that we can now represent uncertain values to some extent anyway using lambdas. And maybe we can have true uncertain values in the grid in the future. We have a research paper about that that's on our website. Next, I'll hand back to Jack, who's going to tell us about a new concept of bidirectional editing in Excel.
I'm going to be talking about spreadsheets and bidirectional editing. Spreadsheets give us a canvas to quickly explore and analyse data. We can take the table of data and filter people by age. The formula will return an array of values that spill into the grid. We can also compute the unique list of countries. The unique formula helps identify inconsistent spellings in the countries. But to correct them, I need to go back to the original table and modify the values directly. Wouldn't it be amazing if I could fix them directly in the output of the formula? What if spreadsheet formulas were bidirectional, so that editing the output propagated back to the input? Our work explores exactly this idea. We start from the simple concept that if a formula returns an exact copy of an input value, why not let the user modify that value in the output? To achieve this, we enrich the spreadsheet with where provenance, a concept from the database community. Our approach tags spreadsheet values with their provenance or origin, and we call these special values portals. Portals flow through calculation, and if we try to apply an operation to a portal, such as addition, we remove the provenance. However, if a portal flows all the way through a calculation and is the result in a cell, that cell inherits the capability to edit the origin described by the provenance. Let's show an example in our spreadsheet prototype. I have the same data as before, including our filter. The filter function passes through elements unmodified, which means portals in the input will appear in the output. Our cell inspector card illustrates this, describing the provenance of the value and highlighting the location in the grid. The concept of highlighting dependent cells already exists in spreadsheets and can be applied to portals. As this cell contains a portal, we can edit it, and the change is propagated back. Portals implement aggregated where provenance, meaning that a single portal can refer to multiple locations. This happens when portals pass through the unique function. Inspecting this value shows us all the locations that hold the value, and we can update them all simultaneously. The act of editing a portal has exactly the same effect as editing the cells described by the provenance directly. The change is made and the formulas recalculate normally. Now the unique formula only returns 5 values because we've removed the different format. Portals are not only useful for helping to fix data, but they are also useful for constructing views on data. I would like to sort the result of the filter and have cells that control whether the data is sorted and in which direction. This is what I have here, and in our spreadsheet, Boolean values cells are formatted as buttons. This works, but I would really like to have a single presentation view of the data while still allowing me to break the calculation up into steps. With portals, this is easy. In a separate part of the sheet, I can reference the output of the calculation, J3, and I can reference the filter age and the sort parameters. I can even use an if formula to conditionally return the ascending option when sorting is enabled. Because the cells hold portals that reference the original sort parameters, I can apply a portal update by clicking the button, and the edit is propagated back to the original. Using spreadsheet recalculation, the view is updated automatically. We can even add a slider format to the filtered age, again using portals to propagate edits back. Moving the slider updates O16, which holds a portal back to the original parameter in cell G2. We make spreadsheets bidirectional using where provenance, but bidirectional editing is a rich research area and has been previously explored in spreadsheets with lenders. This approach tries to compute how to propagate an edit back on a per formula basis and needs specific rules for each function, such as computing the length of a string. In contrast, our approach with portals does not need to know anything about the functions. We rely on functions naturally preserving where provenance because they only copy, remove, or permute elements. This means that our bidirectional approach only works for a certain class of functions, but through a corpus analysis, we find that many commonly used functions are compatible with portals. We think portals are a simple but effective way to add bidirectional editing to spreadsheets and can transform what users can achieve. We invite you to check out our paper, where you'll find examples, a semantics for portals, and an evaluation of how many spreadsheet functions work with portals. Thank you.
Thanks, Jack. And finally, to finish our presentation, we're going to go back to the theme of sheet-defined functions that I spoke about earlier. And Matt is going to present some research that we did on elastic sheet-defined functions. I hope you enjoy it.
Hi, I'm Matt McCutcheon, and I'm going to talk about a method of automatically generalizing spreadsheet functions to variable size input arrays, which we've nicknamed elastic sheet-defined functions. The spreadsheet is by far the most widely used functional programming environment because it's so easy to use, even for people unfamiliar with conventional programming. For instance, suppose we're shopping for a set of foods and the prices are given without tax. We want to compute the total amount we'll pay, including the tax. We just type our starting data into the cells and enter the formulas we want to calculate into other cells. If it's too mind-bending to calculate the tax on all the foods at once, we can do it for the apple and then copy the formula. We have to be a little careful with relative and absolute referencing, but if we make a mistake, it's easy to spot and fix. We can work one step at a time and always see all the data at once, so for a simple problem like this, we never have to think very hard. Now suppose we want to total a lot of shopping lists. Of course, rather than make many independent copies of the formulas, we'd like to reuse them so that if we have to fix a bug in the original formulas, the fix takes effect on all the shopping lists. Since we're familiar with calling built-in functions like sum, can we define our own function for the shopping list that we could call? In current mainstream spreadsheet tools we can, but we have to rewrite the logic in a separate programming language such as Visual Basic, which sacrifices all the usability advantages of spreadsheets. Fortunately, there's an easier approach that has appeared in many research systems, and we think it's only a matter of time before it becomes mainstream, the sheet-defined function, or SDF. To make our original formulas into an SDF, we just mark the cells that represent the inputs and output of the function and give it a name. Now we can call shop on the second list just like a built-in function. Semantically, the tool makes a temporary copy of the function body with our new input substituted in and returns the new output, though of course the tool can optimize this process. The user can open the temporary sheet to see what happened. This requires users to think a little harder, but we think many of them will be comfortable defining SDFs, and the rest will at least be comfortable calling them. However, we quickly run into a problem if we call shop on a shopping list of a different length than the original. When we try to put the pre-tax prices in the input range, they'll get cut off and we'll get the wrong answer. The result we'd like is as if the body of shop were resized to fit the input. How can we make shop behave this way? One approach is to let the entire array of prices be stored in a single cell. If we apply an operator like plus to two arrays, we're implicitly adding the corresponding elements. This will work regardless of the sizes of the arrays. This is a little more for users to learn, but it's a plausible solution for shop. However, for more complex SDFs, the array programming approach becomes unmanageable. Here's a sheet containing the transaction history for a bank account with interest compounded daily. To compute the balance after a transaction, first we apply the interest to the previous balance based on the number of days since the previous transaction. Then we add the amount of the current transaction. This example presents two new problems for the array programming approach. To line up the previous dates with the current dates, we need to shift the array in A4 down one element and add A3 at the top. Let's assume that a spreadsheet tool designed for array programming will have a shift down function to do that. But for the reference to the previous balance, if we tried to do the same thing, we'd end up with the whole array in C4 depending on itself, which won't work. To handle the iteration, we need to use a special function called vscan2 and pass a lambda function that computes each element from the previous one. Most users won't be able to come up with this unless they find an example on the web that's similar enough that they can adapt it to their problem. If that isn't bad enough, here's another SDF with a naive model of cascading delays in a bus transit system. The idea is that a departure from a station will be delayed if the bus that was supposed to make the trip hasn't arrived yet. We want this SDF to resize in three different ways: the number of time steps in the simulation in the vertical direction, and the numbers of stations and routes, both in the horizontal direction. There's mutual recursion among four of the arrays. While we think this is possible to write using array programming, it's going to be such a mess that I won't even try. So it seems we really do want to resize an SDF at the cell level, effectively generalizing it to handle inputs of variable size. We call the result an elastic SDF. Maybe the user could somehow specify how the resizing should work, but it turns out that for many SDFs, including all three we've seen so far, the user doesn't need to do anything because we can figure out the resizing automatically. That's the topic of our paper. Let's see how the generalization process works in the simpler shop example. For the purpose of describing our work, we use a textual notation for SDFs. Users don't need to know anything about this notation, though we have evidence that some users may find it helpful. Here we have the function name and the input and output ranges. Each line of the body describes a rectangular tile of one or more cells with a copied formula. For example, the first line describes these three cells. The given formula is placed in the top left cell and copied to the others with the usual adjustment of relative references. We can now write the elastic SDF that we want in this notation by introducing a length variable alpha that can take any non-negative integer value. Of course, if we set alpha to 3, we get the original shop back. We'll call this elastic SDF shop1 for reference in this talk, though the user would invoke it using the original name shop. When an elastic SDF is called, we set the length variables to match the argument sizes, in this case setting alpha to 6, and substitute them into the definition, giving an ordinary SDF that we can evaluate as before. Note that tiles may collide when they expand. We address this by labeling each reference with the tile or tiles it originally pointed to and having it read only from those tiles, even if others overlap them. Here, the reference in the sum reads the H7 of tile 4, while the output reference reads the H7 of tile 5. We do this for all SDFs, but to reduce clutter, we won't show the labels for the rest of the talk. The question immediately comes up, is the best generalization of a given SDF always clear? For one thing, we want a generalization that's well-defined, meaning that its references stay in bounds for all values of length variables. For example, if we set the height of the column H tile to alpha, but the height of the column G tile to 3, then when alpha increases, the H tile will be referring to undefined cells below the G tile, so this generalization is not well-defined. From now on, we'll consider only well-defined generalizations. To illustrate the next point, consider this contrived sum2 SDF that sums two arrays and adds the totals. Here are two well-defined generalizations. Sum2D allows the arrays to be different lengths alpha and beta, while Sum2S requires them to be the same length alpha. We say that Sum2D is more general than a Sum2S since it can be converted to Sum2S by substituting for the length variables. We prefer Sum2D to make sure we generalize as many degrees of freedom in the original SDF as possible. So given an SDF like SHOP, if there's a well-defined generalization that is more general than all the others, which we call principal, that's the one we want. Unfortunately, there are several problems that can cause there to be no principal generalization. We'll look at one of them. In addition to SHOP 1 that we saw earlier, SHOP has two other contrived but well-defined generalizations, one that uses only the first three items of the input and one that uses only the last three. None of these generalizations can be converted to any of the others by substituting for alpha, and since they can all give different answers on the same input, it should be intuitively clear there isn't a principal generalization that's more general than all three. The user probably wants SHOP 1, but we have to formalize that somehow. So we introduce the concept of a regular generalization, which satisfies several conditions on top of well-definedness, one of which is that a cell reference can't pick three elements out of a larger tile. So SHOP 1 is regular and the other two generalizations are not. Now, out of all the well-defined generalizations of an SDF, if we keep only the regular generalizations, we can prove that there's always a principal regular generalization, and that's the elastic SDF we use. This can be seen as the analog of the principal type of term in a functional programming language. Our algorithm to find the principal regular generalization introduces all the variables it could possibly need, generates constraints on them based on the definition of regularity, and then solves the constraints. For example, because of the relative reference between the tiles in columns G and H, we generate a constraint that the heights of those tiles are equal. Again, this is analogous to a type inference algorithm in a functional programming language. We've seen that in order to have a principal generalization, we needed to introduce a concept of regularity that excludes some well-defined generalizations. We try to make it capture user intent, which inevitably involves judgment calls. Our goals, aside from having a principal regular generalization, are to support as many realistic SDF design patterns as we can, and keep the process predictable for users, even if they don't know the detailed rules. Our work represents the first draft of the definition. We expect that future work will refine it. This is all technically elegant, but we need to make sure we're actually making things easier for users. So we did a user study to compare elastic SDFs to the best existing alternative, namely array programming, on a set of tasks based on real-world spreadsheets we previously collected. I'd like to highlight a few findings. First, users experienced lower cognitive workload using elastic SDFs compared to array programming, based on a standard survey called the NASA Task Load Index. Second, we have partial data suggesting that users solve tasks faster on average using elastic SDFs compared to array programming. And finally, while users stated a preference for array programming for simple tasks, they preferred elastic SDFs for more complex tasks. This is no surprise given that complex tasks are much harder to solve with array programming. These results are really promising, though more work is needed to further optimize the user experience. So, we've seen briefly how we can use ideas from programming language theory to offer spreadsheet users an easier way to reuse logic on inputs of different sizes. You can find the full definitions, algorithms, and proofs in the paper. We look forward to making this functionality widely available to improve user productivity. Thanks for listening, and we look forward to your questions and feedback.